Today I'm excited to talk about a SolidWorks motion study of a simple machine. We're going to develop the theory of a simple machine. We're going to pick the wedge, and we're going to talk about its gear ratio. I use that word generically as ratio of input speed to output speed. We're going to look at mechanical advantage, which is the ratio of output load to input load. We're going to do this both theoretical mechanical advantage, where it's considered frictionless, and we're also going to try to predict the actual mechanical advantage, where we consider friction as well. So we're going to do that theoretically, and then we're going to mod this up in SolidWorks and do a motion study, and then compare the results. So the wedge. In the wedge, we have a nut that goes up based on a wedge that goes right to left. So the input force that pushes the wedge is labeled as PR. The output force is labeled as F, which is what the nut is driving up. And we're going to be considering raising the load. The lead angle, or the angle of the wedge, we label as lambda. Try to talk about quasi-static equilibrium because we are moving, and here I try to keep my loads as I've removed the fixed constraints on the nut and on the wedge. I try to keep the loads so that they equilibrate and go through a common point. We are considering raising, and we're also considering that we are moving. So the gear ratio is defined as the ratio of input speed to output speed, and in the case of the wedge, the gear ratio is actually a constant. We could look at the ratio of displacements of the input to the output over some constant time interval. So as the gear ratio is constant in this case, it's a little bit easier to come up with the gear ratio. And as a matter of fact, you could think about the wedge as a triangle and consider the tangent of lambda in order to get the gear ratio as 1 over the tangent of lambda, since it's going to be the input displacement divided by the output displacement. In a perfect world, the input force, I could call the perfect input force PR with a star. I use the star to denote lossless. In this case, this would be the lowest possible force when there's no losses present. In that perfect world, you'd have the output power, output force times output velocity, would equal the input power, the perfect PR, times the VI. So this means that your theoretical mechanical advantage would be the output force divided by that perfect input force. If you take this equation and divide both sides by PR star and VO, you basically get this. And then you can define theoretical mechanical advantage as the output force divided by theoretically best input force. And that's going to be equal to the VI over VO, or the gear ratio, which is 1 over the tangent of lambda, as we've established. And going back to the wedge, we kind of want to know what our actual mechanical advantage is. You can actually define that as M sub R as the actual output force divided by the actual input force, where you can consider losses such as friction. So in a real world, your output power would be some efficiency times your input power, where eta sub r is the efficiency, and I use the subscript r as we're raising right now. This means your actual mechanical advantage is F divided by PR. You again take this equation and divide both sides by PR times VO, and you'll get this equation. so that you could say your mechanical advantage is F over PR is eta sub R times VI over VO, or eta sub R times G, the gear ratio. And remember that the gear ratio is equal to the theoretical mechanical advantage. So you get a nice relationship that your mechanical advantage to raise, your actual, is equal to the efficiency times your theoretical best mechanical advantage. That's a nice relationship. If we knew the efficiency by testing or some other means, it would basically mean that you could estimate your mechanical advantage to raise by purely knowing the kinematics, the gear ratio, coupled with the efficiency. That's one way to do it. Another way is using statics and some model of friction, which is what we're talking about right now. So if I remove the nut, I actually have a wedge, and I can focus on the free body diagram of the wedge only. And I'm going to focus the friction acting right at the interface and sort of take whatever, if there were any friction on the bottom of the wedge, and force that to be modeled here. So I've taken the nut away, and I'm going to have a normal force in this perpendicular to the wedge face, and then I'm going to have a friction force times that perpendicular normal force that's going to be opposing the right to left motion of the wedge. And again, I have my lambda being the wedge angle, and I still have the output force showing on the wedge in this way. In this case, I'm going to model the static and dynamic friction factors as both being equal to lowercase f. Some people use mu, and that's what they use actually in the SolidWorks. Anyway, so you can go through that free body diagram, and you can come up with actual mechanical advantage to raise is going to be F over PR. And you're going to get it as a function of the coefficient of friction F and the tangent of lambda. And here we're going to avoid kind of some wonky situations, and we're going to say that F is less than 1 and tangent of lambda is less than 1. It's interesting to note that when you set F equal to 0, you actually get M star as being 1 over tangent of lambda. So now we can talk about the efficiency to raise. In this scenario, the efficiency to raise is going to be M sub r divided by M star, and you can show that it's going to be 1 minus F tangent of lambda divided by 1 plus F cotangent of lambda. And again, when F is 0, you actually drop back to eta sub r being 1. So now, theoretically, I'm going to focus on a numerical example where I have lambda is 8 degrees and my friction factor is 0.05. From the preceding development, I get a gear ratio and theoretical mechanical advantage of 7.1154. I get my mechanical advantage to raise as 5.2113, and my efficiency 73%. And sort of getting prepared for SolidWorks, I'm going to load my output with 20 pounds. So that means my theoretically best input would be 20 divided by 7.1154, or 2.811 pounds. By actual, with friction being considered, would be 20 divided by 5.2113, or 3.838 pounds. Okay, I've created a SolidWorks assembly, and I've already actually created some parts, a nut and a wedge in my directory. And so I brought my 2 parts in. I'm going to save the assembly as, let's say, simple 1. That. So I've got my assembly, I've got my nut in here. Change this to ambient backdrop white. Okay, let's see how my nut's configured. So my nut's configured looking like from a right to left wedge action. So let's go with that. First thing I'm going to do is float my nut. Don't like this where the bodies will come in automatically fixed. I like to actually take full control over where my parts are going to be mounted and how they can move. So I'm going to take the nut and free it up, float it, and I'm going to take that face and actually mate it with, let's say, the front plane. How about that? So that looks good. And then I could take this face and mount that or mate that with the right plane. So I like that. So now the nut properly goes up and down. It's constrained properly. So that looks good. So my wedge is kind of a little bit backwards. I can take the wedge, take that face, and make it mate with the front plane, actually the other way. So I like that. Go back and take a front view of this. So we're getting close here. What I want to do is I want to make the bottom face of my wedge, mate that with the top plane. Really close now to what I want. Let's take a look at my mates so far. I've got 4 mates. So that's looking good. I think my nut is configured to go up and down properly, and then my wedge is configured to go left and right properly. So everything's looking good. So far I've got 4 mates. I think I'm going to try to create a linear, sort of a gear mate, if you will. Call it an advanced mate. I think it's linear coupler. So for this one, I want to bring in my theoretical mechanical advantage, or my gear ratio here. I'm going to pick some faces, and I usually have to fumble around here a little bit to get this going, but I'm going to say, okay, let's pick that as my output face, and pick this one as my input face. And I'm going to pick, what was it? G is 71154. 71154. So I'm going to pick that, put 7.1154 there, inches. So that's the ratio of input displacement to output. But it might be backwards, and it might actually go the wrong way. Let's see what we got. Boom. Hit that. So I'm going to go play around with it a little bit. So if I move this, actually it goes the wrong way. So when I move it this way, it goes down. And it looks like it's going too fast. So I've got it the wrong way. Yes, so if I move the output, the input's moving a short distance. It's going the wrong way. Let me fix that first. So edit feature, and I'm going to reverse that. Say OK. Now let's see what we got. Oh, so it looks like it's moving in the correct direction. So if I want to go right to left, the nut's going up. Still looks like I've got that sort of overdrive. So I move the input a little bit, the output takes off. I move the output, the input's moving a little bit. So that's looking like it's backwards. Still right direction. So I kind of have to fight this sometimes. Edit that. So I'm going to swap these faces. So that was, swap this. Put the wedge up here. And the nut down there. Let's try that. Okay, let's try that. So now this looks right. So if I move the nut a little bit, the wedge is moving a lot. Move the wedge a little bit. So if I move the wedge like the distance, I think that's 8 inches, the distance of the width of the nut, then the nut goes up about 1 inch. So I think I'm in good shape now. So I've got linear. Tell you what I'm going to show you here is I'm going to suppress that for a moment. So now that particular mate is suppressed, because what I want to do is I want to get it into a good position where I can start the simulation or the motion study. I'm going to mate that edge to that edge. So it's an edge to edge mate, and it comes out at the bottom. I can actually rename these mates edge to edge, and I could call that gear. So now gear I have is suppressed still. Oh, let me unsuppress that one. Or, I'm sorry, suppress the edge to edge and then unsuppress the gear. Interestingly, when I highlight the gear, you can see that that's showing at 712 and this is showing at 1. That's what I wanted. So when I move this approximately 8 inches, that would get this to go up approximately 1. And it looks like they're in contact, so we're simulating what we want. So that's all looking good. Wonder what would happen if I unsuppress that now. Oh, still happy. Sometimes it'll complain about being over constrained, that kind of thing. If you notice, it's fully defined. And that's exactly what you want before you enter the motion study. So to recap so far, SolidWorks noteworthy. No body should be fixed. You should float them and then can use mates in the coordinate planes or reference geometry to constrain the body movements. Obviously, you can use touching and sliding surfaces of neighboring bodies, those mates, in order to get the bodies where you want them. You can rename and reorder those mates. You can name the initial conditions, ICs, and put them at the bottom. Just a point of reference, mates are frictionless constraints that act during a motion study. If you have a mate that runs during a motion study, it is a frictionless constraint. So that's something to remember as you try to debug. Use the initial conditions to locate the bodies for the launching of the motion study. You want that fully defined on the bottom. And then what you do after we create the motion study, I'll show you how to suppress the initial conditions from there. The only thing we have left is to do an interference check. Just want to stop for a moment and just kind of review the mates that we have and talk a little bit about the importance of the mates. The mates can be arranged. You can actually pick them up and move them around in the tree. The mates that I put at the bottom, I'm very, very particular about those mates. The mates at the bottom, I usually name those mates, and the mates at the bottom actually will be suppressed or not active during the simulation. I use these bottom mates that I name as the initial conditions for the mates. So I actually fretted about some of this stuff. Like I fretted about having edge to edge. That's to sort of launch the nut and the wedge in the simulation with a proper starting location, relative starting location. This gear ratio actually will be suppressed, and we're going to rely on the actual face-to-face contact between the nut and the wedge to simulate the motion. So this gear that I actually fretted about actually won't be used. It's a point of reference I wanted to highlight. These upper four mates, however, will be used. So mates that are not suppressed during the simulation will actually be active. You'll see more about that later. But we're in very, very close to where we want to be when we start the simulation. To do the interference check, you go to Evaluate, Interference Detection, and then you do a Calculate. No interference, so we're good to go. And that's really important to do the interference check, because when you turn on the solid body contact and there happens to be interference at time 0, it causes the motion study to quote unquote explode. And it's a pretty cool sight to see, actually. But anyway, so if you don't want exploding motion studies, you do that interference check. Okay, now I'm just about configured here. One thing that you might do is pick a view that you want. Like if I want this view, oh no, not that one. If I want this view for my motion study, then I can select it before I push this tab. Okay, so let me push the tab and see what happens. So I push the motion study tab, and a motion study is actually being created now. So it takes a second. Okay, so motion study 1, and when I go to this tab, I want to pick motion analysis, and that won't be an option if you don't have the SolidWorks motion preloaded. So if I go down to add-ins, you can see that I have SolidWorks motion checked there and there, so that I can select motion analysis, and that's what I want. So I'm good to go there. First thing I'm going to do is take this diamond, and for this example I'm going to go to 16-second motion study. I'm going to go look at my mates, and as promised, I'm going to take, with the slider all the way to the left, I'm going to take those two mates and I'm going to suppress them. So you can see that those mates are not active during the simulation. Very clear there. You just have the initial diamond that turns them off. And now we're good. We've got what we want. Okay. So now what I'd like to do is bring in solid body contact. So I'm going to pick solid body contact there, that icon, contact. And I'm going to select the nut and the wedge. Okay, so here it's important, even though I'm going to uncheck this material box in just a minute, it's important before I do that I pick aluminum greasy or something besides acrylic. This acrylic on acrylic by default has caused me so much heartache, and I've wasted so much time with parts just going through each other. So make sure that you get away from that acrylic on acrylic. See, it's even crazy because I'm actually going to uncheck it now, and when I do that, I'm actually able to go in and select my friction factors. And I'm actually going to disable damping 0 and 0 out the damping. I'm going to pick the 0.5 for kinetic friction and make that equal to 0.5 for static friction. And the pre-selection of that put of the aluminum greasy, it doesn't show up right now, but the aluminum greasy on aluminum greasy makes this stiffness very, very high when it wouldn't be if I had left that acrylic on. Okay, so I think we're going to be in good shape here for solid body contact perspective. And we've modeled with the 0.05 the value which we had used in our theory. Okay, so I'm going to be good there. Next thing I want to do is put together let's do a force. So I'm going to do a force to retard the output. I'm going to retard that face, and I'm not pulling up on it. I'm going to push down, so it's going to oppose it, and I'm going to put that 20 pounds output, not 220 pounds of output. So that looks good. Right. So looking at it now, I've got my ICs suppressed. I've got my solid body contact. I've got my force. So what I've done is I'm loading the output, and because kinematically I know what the input should be doing, I can move the input. So that's what I'm going to do. I'm going to set up the motor. Motor's right there. So that's a little bit of a fictitious linear motor. And I'm going to select this face here, and I want it to raise, so I need to change that direction. And the width of my nut is 8 inches, so I'm actually going to move 8 inches. And I'm going to do that in 16 seconds. So there's a lot of bells and whistles, a lot of other ways I could do this. Got a lot of options, but for now this is going to achieve our goal. So I've got my motor. I think I'm good to try something here. I'm going to go up here and save it. And then I'm gonna calculate it. So I use this button here to calculate. And just there's other parameters that I could configure, but this is just a basic motion study. You can see that it is working. Earlier the nut was kind of falling into the wedge, but as I said, that was because of that acrylic versus what you don't want. You want the aluminum greasy before you disable it. It's kind of crazy. Okay, so we've got our motion study. Now let's go look at the results of the motion study. So to do that, I want to look at some plots. I'm going to add some velocity plots. I'm going to look at displacement of linear velocity, and I'm going to look at the y component of the top face. Okay, I want to do that. I'll create a new plot. So that's what it looks like. So that's my output displacement. Okay. Then I'm going to create a new plot of my tell you what, I'm going to make that magnitude so it doesn't go negative on me. Alright, so I'm going to pick that face, and that's what we've got. So I've got input displacement, and I've got input velocity and output velocity. There's two different plots. They're down here. I've kind of moved them around a little bit. So this is my output. I can show that. That's the of the nut. And if I go over here to this area, I can go right mouse, export CSV, and it's going to export it as nut. It's going to export it as a CSV file. So that's the nut. And then I can also do this, show plot, I can do this for the input. So that's my wedge. And then what I can do is I can go into my wedge 0 directory. I can bring up my wedge 1 CSV. And so that's the wedge. So that's the input. This is the input. inches per second. Then I can look at the output, open, just copy that column. Kind of want to make sure it's going the right way here for as time versus position or velocity. So I've got 16 seconds at 400 and whatever 3. Make sure that looks good. I think that's right. So we can take that column, copy it, and plop it here. So this is output, inches per second. Right. Make sure the bottom's still well behaved. It is. So we've got the same number of rows and all that business. So I'm going to look at my gear ratio, simulated, dimensionless, and I'm not going to fret the initial parts of this. Might start a little bit after the simulation begins. I'm going to take the input speed and divide by the output speed. Copy that down the whole way. And it's looking pretty good. I could plot it. I mean, I could do so many things here. I could take, just copy that to even it out. Copy by value. So the first part is going to be kind of forced in there. But I could take and plot, insert a scatter plot. So ordinarily it's like the gear ratio is just above 7. So look, there's no spiky stuff after that initial part, and if I remember right, it needed to be 7115. 7115. Okay. Well, one thing I could do is I could just highlight that column and see the average is 7115. That's pretty cool. I could fine tune it. I could go in and do some filtering. I mean, there's so many things. I'll just do an average right now of, say, let's say D50 to D, what was it, 403? Or let's say 400. Something like that. Let's call it that. So copy that value and then go back into my theory, and I'm going to paste it right there. Paste that value. Oh my, it's right on the money. I mean, we can look at relative difference. We could say, okay, equals absolute value of this minus this divided by the theory, let's say. So that is, wow, that's really good, really good. What, are you kidding me? So it's like in the, I don't know how many place we could go scientific on this one, maybe. Yeah. So it's in like the 8th decimal place. I didn't expect that. It's really solid. Just kind of going back to thinking about what we've done here. That whole gear ratio thing is not because of that gear 1. That's suppressed during the simulation. That is due to the solid body contact and the linear motor you have pushing on your input. That's what's giving us that. The solid body contact is giving us that actual gear ratio. I think that's noteworthy. Another plot I can do would be actually seeing what the motor force is. I could pick force. I could pick motor force, and magnitude would be fine here. Go up and pick my motor. Create a new plot. And see what that's coming out as. export CSV, linear motor, that. And then I can open that linear motor, kind of see what that is, and again, looks like it should be 3.838 is what I think we were claiming from theory. Theory said 3.838, what it could be. So what we could do is, again, do the averaging thing. And I'm going to neglect the first ones. I'll go D50 again to D400. Oh crap, not D, B. So we're looking at that column. So it looks like it's 3.8374, so it's really, really close. I copy that and bring it back into my theory page, plop it there, paste the value. So this is SolidWorks. I'll put that column or row as SolidWorks. And then what I could do is do this theory, or I'm sorry, relative difference. Just copy that guy and that guy. Very close, very close. Wow, so it's less than 0.01% difference. That's outstanding. Did not expect that at all. Very nice, very nice. Right. Let's play around with how we could figure out to do efficiency, we kind of need to know this column. You know what I could do is I could go in here and I could duplicate this study. So I'm going to take this guy right here. I'm going to duplicate. I think it's a little bit different in the newer versions. Might be copy paste kind of thing, but I'm going to call that motion study 2. And I'm going to go up to solid body contact. I'm going to edit that feature. I'm at the beginning, so I'm going to edit that feature. I'm going to make this friction just as low as I can. I might go 3, 4, 5, 6, 1. Like that. So a bunch of zeros and then a 1. It might even let you do a 0 right there. 0 friction. But I've got solid body contact with almost 0 friction there. So that's my first thought in how I could do this. Notice I have the separate motion study. When I do a pack and go, it will concatenate all of these. Okay, so I think I'm ready to go, and I'll need to recalculate. Boom, hit that. So my input motor force should be much lower. And I actually would have a plot here to show. Oh, yeah, it's lower. So if I take this and I say, okay, export CSV, it's going to bring it out as a linear motor 2. So I say save. I don't need to go back and look at the gear ratio. That's going to be the same. I could, but I don't think I need to. So I need to think about bringing up the linear motor. Open that guy. And I see the 2.8-ish. That's kind of what theory was telling me for a PR star. So I'm going to do the same thing. I'm going to say equals average. Throw away some. Say B50 to B 400-ish. So I've got that. Got to take that value, cut it or copy it. Put it over here with theory. Paste that value. Show some more decimals. Boy, really nice, really nice. I take that, copy it over here. Same kind of real good agreement here. So efficiency, All right, let's look at mechanical advantage, MR. So this would be equal to my output force, which is 20 in a simulation, divided by my simulated input. So that's really, really good theory-wise, or simulation-wise, agreeing with theory. And I've already got my M star from SolidWorks. So this is what SolidWorks is telling me. And then I could, again, look at my relative difference. Boom. Right there. And it's going to be same order of magnitude. So fractions of a percent. That's really good. So simulated SolidWorks, I would take the simulated mechanical advantage and divide by the simulated theoretical. So right there. I mean, we're looking at fractions of a percent. Let's look at how this differs. So unfortunately, they all look like they're about equal here in the 4th decimal place. I guess I could maybe show another decimal. I don't know. They're so close to being equal, all of these. But you saw what I did, kind of poking around here. So theoretical efficiency 73%, 73.24. SolidWorks reported 73.25. Mechanical advantage, SolidWorks reported 5.2117. Theory 5.2113. Very little difference. SolidWorks theoretical mechanical advantage 7.1154. You have to show, well, again, this one was to the 8th decimal place, so very, very, very good agreement all the way around here on this. So this is the summary of the 0.05 friction factor with lambda equals 8 degrees. From theory, I got these numbers that I had to actually take out to more decimal places. That was gear ratio, theoretical mechanical advantage, actual mechanical advantage, and then efficiency for raising. In the example, I did 20-pound force on the output, and I got my theoretical input as that, and my actual input is that from theory. And then in SolidWorks, I showed you step by step how I got these numbers, and it turns out that they're very, very close to what theory. So very good agreement is what I got in this. So noteworthy number 2. So when you create your motion study, whatever view you have before then is sort of the one that is what you launch with on the motion study. And that can be changed later, but that's just something I thought I'd mention. Another thing is diamonds, knowing what they mean. I'm going to show you a good, fun example of diamonds in just a minute. But generally speaking, for machines, you design from the output going backwards. So you think about there's a certain load and a certain displacement, a certain speed that you need that output to do, and then you kind of start from the output and work backwards. And that's what we did. We loaded our output with the 20 pounds. And if you propose the kinematics, and by that I mean setting the gear ratio, if you propose a gear ratio like we did with the 8 degrees, and then there's no slip, so that means you actually know the input motion, the proposed input motion for the output that would be desired. And what we saw here was that we load the output and move the input. So that's an important thing I can tell you. So I thought I might show you a couple of things, a couple more things. I could take this motion study 1 and duplicate it, and that's the one with the friction in it. And I wanted to show you this diamond thing. I could take and extend this motion study, say 2 more seconds, and I can come back and I'm going to try to put a diamond on the motor. at 16 seconds. I'm going to go place a key there, and what I'm going to do is I'm going to turn the motor off so you can see what's going on here, that the motor is going to be active for the first 16 seconds of the simulation. This is the third motion study now, so I'm not altering the first one. So I'm on the third one, and I'm going to see what happens here. I'm going to have some fun with this. So what I see when students struggle with motion studies is they'll have diamonds everywhere. What they're doing is they're making changes with the slider somewhere other than the beginning or where you want to put that diamond. So good, important thing to mention. So now let's see what happens. Remember, this is with a friction factor of 0.05. So what I'm going to do is I'm going to do a new study of this, see what happens. At the end, at 16 seconds, see what happens. Oh, boom! Well, that was wild. Yeah, so what happened is, at 16 seconds, the motor let go, quote unquote let go, and the nut fell, and this was a classic back driving scenario. And it has to do with when you look at lowering the nut, it has to do with what the friction factor is for it. And if it is less than the tangent of lambda, it's going to be back drivable. If I make it more than the tangent of, this is for lowering, let's say 0.2. I'm going to do 0.2 being more than the tangent of lambda, and it might stick. That should be self-locking when I let go. So I'm going to rerun this, and I could duplicate and create a new one, that kind of thing, but just kind of having fun. I'm going to take this all the way to the beginning, and I'm going to change my solid body contact friction to 0.2, and it should stick this time. Come down here instead of 0.05, I'm going to go 0.2, 0.2. Okay, do that, and then I'm going to calculate it again. See what happens at 16 seconds. Motor let go, and you can actually see that the simulation is making sure. Simulation really doesn't run in real time, so right now it's simulating and making sure that it is sticking by the solid body contact interacting between the two bodies. So no motor, so let go, so have that force, self-locking because of that tangent of lambda and the friction being less than the friction factor. So very interesting thing. Of course, what I want to do now is I want to save all my work. File. I'm going to save it. I've got 3 motion studies here. And what I want to do, if I want to upload this, my work, I can do pack and go. And under the pack and go, I want to include simulation results. And I want to save it to a zip file. I'm going to go simple1.zip. Usually flatten to a single folder, but there's no nested folders here, so it just has the 2 parts and then the assembly. And simulation results, make sure that's checked. I think I'm good. So it's going to save it in that folder. Go look, and it should have all 3 motion studies in there. So when I go look, yeah, it's looking like it's at 1007. That zip file is my pack and go, and it should have the assembly and the 2 nuts in there. The assembly should be kind of big because it has the motion study results in it. Yeah, so it's looking good. So that's what I would actually upload. So in summary, we looked at a simple machine, a wedge. We looked at the theory of it. We talked about gear ratio. We talked about mechanical advantage, actual and theoretical. Then we looked at SolidWorks, doing a motion study in SolidWorks to get simulated versions of gear ratio and mechanical advantage. We heavily relied on solid body contact and also loading the output with our force, and as well as a linear motor to move our input. So that's all for today. I hope you enjoyed it.